The first law of thermodynamics shows us that the internal energy of a system changes through heat flow into or out of a system. So we represent that with the internal energy U is equal to Q, the heat, plus W, work. Now Q will be positive when the flow is into the system. Q is negative when it is out of a system. W is positive if work is done on the system. So work on the system. W is negative when work is done by the system. So work ends up being done on the surroundings. This is called a state function. Now, a state function is where the value is only dependent on the state of the function that is in. It's not dependent on the pathway, the way it got there. So if we were to take an elevator, we were going in a building, just pretend this is a building for me, and we get on the elevator at the ground floor. And when we're done, we end up, so if this is 1, 2, 3, we end up on the 4th floor. Now that elevator, all that matters is that we went from ground 1 to ground 4. It doesn't matter that the elevator actually went all the way up to the roof, then back down to the 3rd floor, and then up. That pathway is not relevant to a state function. All that matters is that you went from the ground floor to the 4th floor. Now in chemistry, we use a value called enthalpy. Enthalpy is abbreviated with an H. Now H is equal to U, the internal energy, plus what's called pressure volume work. Now I don't want to get into derivations or anything, so we're just going to kind of ... What we learn is that the change in enthalpy is equal to the heat of a reaction at a constant pressure. Now when we use delta H, we will oftentimes have delta H defined after a reaction. For example, if I have 2 moles of hydrogen gas reacting with oxygen gas to form 2 moles of liquid water, let's do liquid water now, then the delta H for this reaction would be shown as a value. Here it's negative 572 kilojoules. The negative sign indicates that this is an exothermic reaction. That means that heat is given off. So you have to notice how the moles are written. So this value is appropriate for creating 2 moles of liquid water from 1 mole of oxygen and 2 moles of hydrogen. Multiply all of these coefficients by half so that we ended up like this. Then the value of our delta H would also be in half. So this is an extensive property. Now notice when we're talking about energy, using a half for a coefficient is okay. It's not ideal, but it is okay. Now delta H is dependent on the phase of matter. So what I want to call your attention, liquid water. We could also have gaseous water. So if I have gaseous water, if the conditions are appropriate for that, I still have the same reactants, but then I have a gas here. My delta H is different. We'll get into that further later, but my delta H is negative 242 kilojoules. So you have to pay attention to the phase of matter as well as the moles of your reactants and products. So let's take this concept a little bit further. If I have 0.0500 moles of HCl, and that's aqueous, and I'm going to react that with 0.0500 moles of sodium hydroxide, also aqueous. And when I have that, 2.9 joules of heat are produced. Then what is the delta H for 1 mole of acid that reacts with 1 mole of sodium hydroxide? Well, we can look at this a couple of different ways, but what I want you to do is use this relationship here as a conversion factor. So if I have 2.9 joules, and that's produced with 0.0500 moles of HCl, then I can just divide these numbers here and that's kilojoules. I can divide these numbers here, and then the units I get are kilojoules per 1 mole. So for 1 mole of acid, the delta H is then a negative 58 kilojoules. So I could also perform this reaction or this calculation like this. I start with the 1 moles of HCl that I'm looking for, and I know 2.9 kilojoules are produced from 0.0500 moles of acid. So I can do the calculation this way, just end up with moles. I'm sorry, just end up with kilojoules. So let's try another one. If we have 1.34 grams of zinc, and that's going to react with 60.0 milliliters of 0.750 capital M moles of HCl. That's going to produce 3.14 kilojoules of heat. So what is the heat for 1 mole of zinc? And that's going to react like this. So we have our solid zinc, and that's going to react with 2 moles of HCl, and that's going to be aqueous. That's what this is. And that will react to form zinc chloride, aqueous, and hydrogen gas. This is a gas evolution reaction. Double check that we are balanced, and we are. So now we're going to convert our grams into moles. So 1.34 grams of zinc. Go to the periodic table for the atomic mass, and 1 mole of zinc has a mass of 65.38 grams of zinc. So that gives us 0.0204. I'm going to give you way too many digits here. And that's moles of zinc. Well, I want to find out how many moles of HCl I have as well, because we don't know if something's limiting, so we better check. Now, I know I have an excess of the HCl here. It's a good practice to just double check that, and I know it's excess because I need twice as many moles of HCl as I do zinc, because the ratio is 1 to 2. And 0.045 is more than twice 0.020. So we do have an excess here of our HCl. So now I'm going to use that energy as a conversion factor. So if I was asked to calculate for 1 mole of zinc, and I had 3.14 kilojoules, and I did say it produces, so that is a negative value. So when it produces heat, and it produces that heat with, let me scroll back up just a smidge, 0.02049, and I'm going to keep that in my calculator, so there are way too many digits there. So the moles of zinc cancel, so I will produce with 1 mole of zinc 153.20 kilojoules, and that is negative. And then we need to look at our significant digits. I believe we had 3 sig figs. We did in our mass, so we can only report 3 significant digits. So it would be 153 kilojoules is the delta H for 1 mole of zinc. Now the negative sign indicates that it is produced. This means this is an exothermic reaction. Now when working with enthalpy, we can get specific. And we have a term called the standard enthalpy of combustion. So the standard enthalpy of combustion is abbreviated delta H 0 with a C. The C indicates combustion. Remember, combustion is burning in an oxygen environment to produce carbon dioxide and water. And this little circle right here, this indicates standard. So this is the enthalpy change when 1 mole of substance burns under standard state conditions. This is called the heat of combustion. Now, standard state conditions are typically 1 atmosphere of pressure, or about 1 atmosphere. It's actually 100,000 pascals, which ends up converting to about 0.98 if memory serves, but we call it 1 atmosphere, and it's usually at room temperature at 298 Kelvin. But this standard state, we can show this combustion with the burning of octane, and we can consider gasoline effectively octane. It's not, but for all intents and purposes, that's what we're going to call it. So if we have liquid octane reacting with gaseous oxygen, then we can combust it with this equation. And the delta H, the standard heat of combustion here, is negative 5,460 kilojoules. So a lot of heat is given off. This is an exothermic reaction. And we can use this as a conversion factor because this is negative 5,460 kilojoules of heat is given off for 1 mole of octane. Remember, the absence of a number here is not 0. The absence of a number is 1. So what is the heat produced by burning 1 liter of gasoline, which we're going to call octane? The density is 0.6925 grams per milliliter. And we're going to assume that gasoline is this C8H18. So we're going to start with our volume, our 1.00 liter of gasoline. And then we're going to use the density to convert that into a mass. But since our density is in milliliters, I'm going to convert this into milliliters as well. Now I can use that density. Remember, the number stays with the unit on top. So now I have a mass of gasoline. I need to convert that into moles. So I calculate the molar mass of this compound. Remember, carbon is 12.01, and I have 8 of them. Hydrogen is 1.01. That should be a 1. And I have 18 of them. So I multiply those things together, and I add them up, and I get the molar mass, or the formula mass is 114.26 grams of C8H18 is 1 mole of C8H18. So I get these numbers here from the periodic table. These are the atomic masses. Just want to make sure everybody's clear where I'm getting that number. Now I can use this value here. So the energy given off, negative 5,460 kilojoules, is for 1 mole of C8H18. So when I perform this arithmetic, and that's multiplying all of the numbers on the top and dividing it by the product of the numbers in the denominator or on the bottom, I get a negative 33,061.74 kilojoules. Go back and look at my significant digits. I have 3 significant digits in my measured quantity here, so I can only report 3 significant digits. So I'll report this as negative 3.31 times 10 to the 4 kilojoules. And that is how much energy is given off by 1 liter of gasoline. We also have a value called standard enthalpy of formation, and that is abbreviated delta H, little circle on top indicating standard with an F. The standard enthalpy of formation is the enthalpy change for a reaction where exactly 1 mole, this is important, 1 mole of pure substance is formed from its free elements in their most stable states. Now, again, this is under standard conditions, and standard conditions are typically accepted to be 1 atmosphere and 298 K. Now, these values are tabulated for us. And these values, let's see if I can bring that up real quick. These values are found on this file. Now, I do update this file as new data is made available. So the numbers that you see in the video may be different from the numbers in this file in your classroom because I do adjust them as new data is made available. So as of this recording, the standard enthalpy of formation of, say, aluminum oxide found right here on the table, the standard enthalpy of formation is a negative 1,669.8. And you see the units up here are kilojoules per mole. So your substances on this particular document are laid out in alphabetical order of the primary atom. You see carbon has an awful lot because there are some organic substances in here. For example, C6H6, which I don't necessarily expect you to know what that is, but you should be able to find it by the chemical formula. That is benzene. Benzene has a delta H of 49.1. It is a positive value. So the heat of formation of benzene then is 49.1 kilojoules per mole. So we can use this table when we perform calculations, and especially when we're finding the delta H of the reaction. Now the delta H of the reaction is going to be the sum of N times the delta H of formation of the products minus the sum of the moles times the delta H of formation of the reactants. Now that's a lot of words for this concept. So if I have a reaction, and I'm going to start with one that's not necessarily simple intentionally. So if I have this reaction here, and remember the phases are important, you do need to make sure that what you're looking at is balanced. That's important. Then what I'm going to do in order to find the delta H of the reaction is look up the H of formations of, I'm going to start with my products. So I'm going to start with aqueous nitric acid. So I'm going to go down here to nitrogen. And I'm looking for nitric acid. And it's important to get the phase correct. Here's aqueous nitric acid. Now the delta H, or the H of formation, which is in the first numerical column on this particular form, is negative 207.4. So what I'm doing is I'm looking for the HNO3. I'm going to add that to the NO. So these are my delta H of formations. Then I'm going to subtract. Maybe that'll be easier. Again, delta H of formation. So my nitric acid, aqueous, was a negative 207.4. And I'm going to add that to the delta H of formation of NO. So I need to find the NO and the phase. The phase, this was gaseous. So again, I'm looking right here. 90.25 is the value that I'm going to carry over. Then I need to multiply each of these by the stoichiometric ratio in the chemical equation so that what I'm left with is just kilojoules. So here I have my NO2, and that's gaseous as well. So I need, oh, it happens to be right below. So I have 33.2 plus, and then I have liquid water. I'm actually going to do a quick search here. So liquid water is found up here. Oh, that's not liquid water. That is actually, this one here is hydrogen peroxide, H2O2. So I'm looking for liquid water, which is right here, negative 285.83. I perform the calculations here, combine, and I get a standard enthalpy of reaction is equal to a negative 138.6 kilojoules. I only go to the 10th place because I only have a 10th place in these values here. So negative 138.6 kilojoules. Now let's try another one. So if we have Fe2O3, and that's a solid, reacting with 3 moles of hydrogen to form 2 moles of solid iron and 3 moles of liquid water. In order to find the delta, I do that all the time. In order to find the delta H, the standard enthalpy of the reaction, I need to find the H of formation of my products multiplied by the stoichiometric coefficients found in the balanced chemical equation minus the reactants, or the sum of the reactants. Now, here's going to be an interesting one, and I'm going to show you on the table first. So first, I'm going to look up iron. So iron in the solid form, that happens to be the lowest energy state. This is the elemental form of iron. And because of that, the heat of formation is 0. Then we have liquid water, which we actually looked up in the previous problem. So I'm just going to take that number here. Then I'm going to subtract. I need Fe2O3. Fe2O3 happens to be right here. So that's a negative 824.2 as of this recording. And then I have 3 times the formation of hydrogen. Now, this is the elemental state of hydrogen. And because of that, the delta H is 0. You may have to simply know that. It's possible that the elemental state's delta H will not be given to you on a quiz, in which case you're expected to know that that is not only is that the elemental state of the element, but that its delta H is 0. The heat of formation is 0. So when I perform this operation, 3 times a negative 285.83, I get a negative 857.49. And I'm going to subtract a negative, which means I'm going to be adding 824.2. So when I perform this, I get a negative 33.29 kilojoules, and really that should be to the 10th place. And that is exothermic. It is exothermic because the delta H is negative. Now again, because the delta H of formation is listed as kilojoules per mole, and we are multiplying by the stoichiometric coefficients here, which are moles, then those moles are canceling out. So all we're left with is the kilojoules. Let's try another one. So if we have silicon, and this is solid silicon, plus 2 moles of gaseous chlorine to form our silicon carbide, then we need to, in order to find the delta H of this reaction, we need to find the H of formation of the silicon chloride minus the H of formation of silicon plus 2 chlorine. Now here, so we're looking for silicon, and I'm looking for the silicon chloride, which we're told is a gas, so it's down here, negative 662.75 as of this recording. And then I'm going to subtract. Now both of these are in its elemental form, so that is going to be 0. If you can't remember and you have a chart, you're always welcome to look it up. Here's solid silicon here. So the delta H, the standard delta H of the reaction, is then the equivalent to the H of formation of silicon chloride, which is negative 662.75 kilojoules. So you see here is our compound, and it's being comprised, or it's being formed by adding up these constituent elements in their most common form or in their most stable form. So if we take something like this compound, and at this point I do expect you to know how to name any compound that you see a chemical formula for, especially an ionic one. Remember that oxygen has a standard form, and it's a 2-. There are 3 of them, which means we have a 6- from the anion side. We have 2 chromium, so in order for this to even out, that means because we have 2 of them, this must be a chrome 3. So this is chromium 3 oxide, and it's reacting with hydrogen gas in order to form chromium, elemental chromium, and water. So in order to find the delta H naught of the reaction, excuse me, I need to find the HFs of my products added together, because it's the sum of the products minus the sum of the reactants. Now again, we need to pay attention to the phases here. So chromium, elemental chromium, is going to have an HF of 0 because that is its elemental form. We've looked up water already, so I'm just going to bring that down. Now this chrome 3 oxide is found under the chromium tab, and here we have solid chrome Cr2O3s, and it's a negative 1139.7. That's supposed to be an S. I realize that probably looks like a G. So negative 1139.7. And then we have our elemental form of hydrogen. So the HF for that is going to be 0. So when I work this through, I'm subtracting a negative, so I'm adding 1139.7. Now, because we only go to the 10th place here, our answer can only be in the 10th place, so I have 282.2 kilojoules. This is an endothermic reaction. It is endothermic because the delta H of the reaction is positive.